Welcome to AI Research Weekly, the show that cuts through the noise and gets straight to the most impactful developments in artificial intelligence. I'm Nova, and with me, as always, is Onyx.
And I'm Onyx. This week, we're diving deep into some fascinating advancements across multimodal LLMs, agentic AI, and crucial new evaluation paradigms. We've seen a surge of activity around bridging the modality gap in MLLMs, pushing for truly unified multimodal models and bringing engineering rigor to the wild west of agent development.
That's right, Onyx. It feels like we're constantly talking about multimodal. But this week, one paper really highlighted a core challenge that's been lurking under the surface. It's titled Reading Not Thinking: Understanding and Bridging the Modality Gap When Text Becomes Pixels in Multimodal LLMs. That title alone is a great hook.
It certainly is. The key contribution here is a really incisive diagnosis of what they're calling the modality gap. Basically, MLLMs, despite being adept at visual understanding, often struggle when text is presented to them as images rather than as raw textual tokens. They found that performance on math tasks could degrade by over 60 points on synthetic renderings when the input shifted from text to image.
60 points? That's not a subtle drop, that's a collapse. So what's actually happening there? Are they losing context, or is it something more fundamental about how they process pixels versus encoded tokens?
The paper attributes it primarily to what they term reading errors. These are failures in calculation or formatting, distinct from deeper knowledge and reasoning errors. It seems the visual processing pipeline, even with powerful models, introduces specific bottlenecks when extracting information from text within an image. They even showed that rendering choices, like font and resolution, could impact accuracy by as much as 47 percentage points on certain tasks. That's a huge confound.
Wow, so it's not just about the content of the text, but the style of its presentation. That's a big deal for practical applications, especially when dealing with diverse real-world documents. What did they propose to bridge this gap? Because understanding the problem is one thing, fixing it is another.
Exactly. Their solution is quite elegant, a self-distillation method. They train MLLMs by pairing the image input of text with the model's own pure text reasoning traces. Essentially, they teach the MLLM to see the image as if it were the pure text input it was originally trained on. The results are impressive. On GSM-8K, this method boosted image mode accuracy from 30.71% to a staggering 92.72%. Crucially, it generalized to unseen benchmarks without catastrophic forgetting.
That's a phenomenal improvement. A threefold increase in accuracy is not to be sniffed at. But I have to ask, does this truly bridge the modality gap, or does it just make the models better at reading? My concern is that while it improves parsing text within images, it might not address deeper issues if the visual information itself is integral to the reasoning, beyond just presenting characters. What if the text is embedded in a complex visual scene, where understanding the visual context around the text is key?
That's a fair challenge, Nova. The paper primarily focuses on text presented as images, rather than text deeply integrated with a visual scene that requires complex visual semantic reasoning. However, by making the foundational reading aspect robust, it lays a better groundwork. If the model can reliably extract text from pixels, it can then presumably leverage that information more effectively for broader multimodal tasks. It's removing a significant impedance mismatch that was clearly hampering performance. It reminds me of the early days of OCR, but at a reasoning level.
I get that. Improving the base-level parsing is critical. It feels like a necessary precursor to more complex multimodal reasoning. Speaking of multimodal, another paper that caught my eye this week, Cheers, Decoupling Patch Details from Semantic Representations Enables Unified Multimodal Comprehension and Generation, seems to take a different stab at unification.
Yes, Cheers is a really interesting architectural contribution. The core idea is about creating truly unified multimodal models that handle both comprehension and generation across modalities efficiently. Their key innovation is decoupling patch-level details from higher-level semantic representations.
Decoupling, you say? How does that work, and what problem is it solving? Because typically, in vision transformers, you're trying to integrate those patch embeddings deeply.
Right. In many current unified multimodal models, UMMs, there's a tension between capturing fine-grained visual details, essential for high-fidelity generation, and abstracting semantic representations, crucial for robust understanding. Cheers addresses this by processing them somewhat separately. It uses a gated detail residual mechanism. This stabilizes semantics for understanding tasks while ensuring that the high-frequency visual details can still be injected when generating images.
So they're essentially creating a more flexible internal representation, allowing the model to choose how much detail to pay attention to depending on whether it's trying to comprehend or generate. What are the practical gains?
Precisely. On the efficiency front, Cheers demonstrates a 4x token compression. This is huge, as it allows for much more efficient high-resolution image encoding and generation. And despite this compression, it achieves comparable or even superior performance to existing advanced UMMs like TAR 1.5b, but with only 20% of the training cost. This is a significant leap in resource efficiency for unified models.
20% of the training cost is a game changer, especially for models this complex. But I'm still probing the unified aspect. Is this truly a single coherent model for all multimodal tasks? Or is it more like two specialized paths that are very tightly integrated within a single framework? How well does this decoupling generalize when you start introducing even more modalities beyond just vision and language?
That's a crucial distinction, Nova. While the paper highlights unified comprehension and generation within vision and language, its elegant decoupling approach is certainly promising for broader multimodal integration. The idea is that by having a more modular way to handle different levels of detail and semantic abstraction, you can potentially integrate other sensory inputs like audio and process their specific details while maintaining a consistent semantic core. It's a step towards general-purpose multimodal intelligence without having to brute force cross-attention everywhere. The efficiency gains alone will drive adoption for current VLM use cases.
That's a compelling vision. Shifting gears a bit, let's talk about the increasingly important field of agentic AI. We see a lot of excitement, but also a lot of talk about reliability and consistency issues. Test-driven AI agent definition, compiling tool-using agents from behavioral specifications, seems to tackle this head-on.
This paper introduces a much-needed dose of software engineering rigor into agent development. The core problem they address is that current LLM agent development practices often suffer from silent regressions, undetected tool misuse, and policy violations. TDAD treats agent prompts and configurations as compiled artifacts, meaning they're systematically tested against specifications.
That's a significant departure from the more iterative, prompt engineering-heavy approach many are taking. What exactly does TDAD entail? How do they compile an agent from specifications?
They achieve this through a test-driven approach. You define behavioral specifications for your agent, much like you would for traditional software. These specifications are then used to automatically generate tests. The agent's prompt, its tool definitions, and its overall orchestration are iteratively refined or compiled until they pass these tests. It's about shifting from an opaque black box prompt to a more verifiable white box artifact.
So it's about explicitly stating desired behaviors and then ensuring the agent adheres to them. What kind of success rates are they seeing with this compilation?
They achieved a 92% V1 compilation success rate with a 97% mean hidden pass rate across 24 independent trials on their spec suite core benchmark. What's even more impressive is the regression safety. Evolve specifications maintained a 97% regression safety score and 78% V2 hidden pass rates, demonstrating that as you modify requirements, the agent remains stable on previously validated behaviors. They also effectively address specification gaming, ensuring the test suite could detect faulty prompt variants with 86 to 100% mutation scores.
97% regression safety for agentic behavior is a huge number. That's something traditional software development environments strive for and often struggle to achieve. But I have to challenge this a bit. How practical is it to write exhaustive behavioral specifications for highly complex, open-ended agentic tasks? Agents are often prized for their emergent capabilities and ability to handle unforeseen situations. Doesn't this test-driven approach inherently constrain that?
That's a valid critique, Nova. For truly open-ended creative tasks, exhaustive specification might indeed be challenging. However, for many enterprise and healthcare automation scenarios, which the paper specifically mentions, the behaviors are intended to be constrained and auditable. Think about an agent managing financial transactions or clinical workflows. You absolutely need verifiable adherence to policies and tools. This isn't about stifling creativity, but ensuring safety and reliability where it's paramount. It's bringing the benefits of formal verification and test-driven development to LLM-powered systems.
Okay, I see the nuance there. For structured, high-stakes environments, this is incredibly valuable. It addresses a critical recurring problem we've identified around the reliability and verifiability of agentic systems. It gives me a bit more comfort knowing that there are frameworks emerging to make these systems robust.
Absolutely. And speaking of robustness and evaluation, another significant paper this week is LME Long Horizon Memory Embedding Benchmark. This work addresses a glaring gap in how we evaluate memory capabilities in LLMs and embedding models.
Long horizon memory has been a persistent challenge. Context windows keep growing, but true long-term recall and reasoning remains elusive. What makes LME be different from existing benchmarks like MP?
LMEB is a comprehensive framework specifically for evaluating embedding models in complex, long-horizon memory retrieval tasks. It spans 22 datasets and 193 zero-shot tasks, covering 4 distinct memory types: episodic, dialogue, semantic, and procedural. The crucial finding is that LMEB and MTEB exhibit orthogonality. This means that performance on traditional passage retrieval benchmarks often doesn't generalize to long-horizon memory retrieval.
That's a surprising and frankly sobering result. We often assume that a good embedding model is universally good. So a model could score high on MTEB but fail miserably when trying to recall information from a conversation that happened 20 turns ago?
Exactly. Their evaluation of 15 widely used embedding models revealed that larger models do not consistently perform better in long-horizon memory retrieval tasks. This is a significant finding that challenges the bigger is always better scaling laws we've often observed. It implies that simply throwing more parameters at an embedding model won't necessarily solve the long-term memory problem. There's an architectural or training methodology gap that needs addressing.
That's a critical insight for anyone designing systems that rely on long-term memory. It suggests we need fundamentally different approaches or specialized architectures for memory-intensive tasks, rather than just scaling up general-purpose embedding models. What are the implications here for researchers working on memory architectures?
For researchers, it highlights the need for dedicated research into memory architectures that are optimized for long-horizon context, not just short-term relevance. It also means we need new training paradigms and objective functions that explicitly reward long-term recall and consistency. The benchmark itself provides a standardized, reproducible framework for this, using both AI-generated and human-annotated data, which is essential for accelerating progress. It's forcing us to acknowledge that memory isn't a monolithic concept in AI, just as it isn't in humans.
So it's not enough to just store information. You need to store it in a way that's retrievable and usable across extended temporal dependencies and different semantic contexts. This makes me wonder about the nature of forgetting in these models. Is it about the embedding decaying over time, or the retrieval mechanism failing to surface it?
The paper implies it's often a combination of both. Embeddings might not encode the temporal or relational context effectively enough for long-horizon retrieval, and the retrieval mechanisms themselves might not be optimized for searching through vast, temporally disparate memory stores. It underscores a persistent problem we've seen. Models often struggle with continuous updates and audits to maintain relevance and compliance across long periods, which relates to the recurring problem of high demand for continuous updates and audits mentioned in our intelligence brief. LMEB is a crucial step towards quantifying and addressing that.
That makes a lot of sense. We've covered a lot today, from diagnosing and fixing reading errors in multimodal LLMs to building more efficient and unified vision language models, to bringing test-driven development to agentic AI, and finally, getting a more rigorous handle on long-horizon memory. It's been a week of deep dives into fundamental challenges.
Indeed, Nova. The overarching theme I'm seeing is a maturation of the field, moving beyond just achieving impressive headline numbers to really understanding why models fail and building robust, verifiable solutions. The emergence of precise error categorizations like reading errors and rigorous evaluation frameworks like LMEB are critical signs of this.
I'd agree with that. It's less about raw scale and more about targeted, principled engineering and deeper theoretical understanding. We're refining our tools and methodologies, which is essential for the next wave of impactful AI systems.
Looking ahead, I'm particularly keen to see how the modality gap findings influence the next generation of truly multimodal benchmarks. If reading errors are so prevalent, current benchmarks might be underestimating reasoning capabilities simply due to input format.
And I'll be watching for advancements in agentic AI beyond just tool use, specifically how frameworks like TDAD might evolve to handle more dynamic human-like goal negotiation and adaptation in open-world scenarios. How do we specify that behavior?
Challenging questions, as always. That's it for this week's AI Research Weekly. Join us again next time for more insights into the bleeding edge of AI.
Thanks for tuning in.